Good morning, students. Today we will discuss some important properties of the first fundamental form. So the first property of first fundamental form is that this form is a positive definite quadratic form in du and dv. So in order to discuss this property, firstly let us define what is positive definite quadratic form. So let us take a real quadratic form given by q, which is the function of variables x1, x2, x3 and xn. This real quadratic form is called positive definite form if q is greater than or equal to 0, means this is non-negative, and this quantity is 0 if and only if all the variables x1, x2, x3 and xn they takes value 0. So if these two conditions are satisfied, then we say that this quadratic form is positive definite quadratic form. Now we will use this definition in our first property. So we will prove that the first fundamental form, which is also called metric, that is the positive definite quadratic form. Now the first positive definite form, that is given by E du square plus 2f du dv plus g into dv square. Now we can write this expression by multiplying and dividing by E. So we get 1 by E. Inside of the brackets, multiplying by E, we get E square du square plus 2ef du dv plus eg dv square. Now in this expression, let us add and subtract the term f square dv square. Now after adding and subtracting this term and combining the terms which makes the whole squares, now these three terms e square du square, 2ef du dv and f square dv square, these three terms makes a whole square which is edu plus f dv whole square, and combining the last two terms with dv square, their coefficients are eg minus f square. Now in this quantity, by using the relation which we have studied among the coefficients e, f, g and h, now h square is eg minus f square. So we can put the value here and we get 1 by e into edu plus f dv whole square plus h square dv square. Now the expressions in the bracket, they are in the form of squares, and so these are non-negative quantities. Also h square is a positive quantity, so this whole expression is non-negative. So we have proved the first condition of positive definite quadratic form, means we have proved that this expression that is greater than or equal to 0 for all the real values of du and dv. Now let us take the second condition, in which we take the form is equal to 0 and see all the variables are 0. So let us now consider this expression e du square plus 2f du dv plus g dv square is equal to 0. When we take this expression is equal to 0, it means this quantity will be 0. Now this quantity is a sum of two non-negative quantities. So if the sum is 0, both quantities will be individually 0. So let us put these two terms 1 by 1 is equal to 0. So edu plus f dv whole square is equal to 0, and the second quantity h square dv square, that is also 0. Now this quantity is non-negative quantity, so this is equal to 0 means edu plus f dv is equal to 0, and also because h square is not equal to 0, that is positive quantity, so if this expression is 0, it means dv will be 0. Substituting dv is equal to 0 here, we get edu is equal to 0. But e is also not equal to 0, that is positive quantity. So from here we get du is equal to 0 and dv is equal to 0. Thus we have proved that the metric, means first fundamental form, e du square plus 2f du dv plus g dv square, that is positive definite quadratic form in du and dv. So this was the first property of first fundamental form. Now we discuss the second property, which is invariance property. Invariance means unchanged. The metric is invariant under a transformation of parameters. Means if in the first fundamental form we apply a transformation on the parameters u and v, then the new form obtained, that is same as the form which was corresponding to the parameters u and v. So let us prove this property. This property is called invariance property. So let us consider the equation of the surface having the parameters u and v. Suppose we apply a transformation on these parameters, and after applying the transformation, these two parameters u and v are transformed to the new variables which we have taken u dash and v dash. And the transformation we have shown by these two relations. U dash is equal to function of u and v. For the function we have taken the symbol phi, and v dash is equal to psi of u and v. So this 2 denotes the transformation to the parameters. New parameters are u dash and v dash. Now to find the corresponding fundamental form, let us find e dash, f dash and g dash. Now to find them we require r1 dash and r2 dash. Now r1 dash means the partial derivative of vector r with respect to the parameter u dash. Now because r is a function of u and v, by chain rule doing the differentiation, so curl r by curl u into curl u by curl u dash plus curl r by curl v into curl v by curl u dash. Now this is vector r1 and this is vector r2. So substituting the values, we have obtained curl r by curl u dash, which is r1 into curl u by curl u dash plus r2 into curl v by curl u dash. Now let us find r2 dash. r2 dash means the partial derivative of vector r with respect to the second new parameter v dash. Now again by using chain rule of differentiation, this is given by curl r by curl u into curl u by curl v dash plus curl r by curl v into curl v by curl v dash. Substituting the values here, so we get r2 dash. Now let us find du and dv in terms of the new parameters. Now we can say u and v are the functions of u dash and v dash. So du can be written as curl u by curl u dash into du dash plus curl u by curl v dash into dv dash. In the same way, let us find dv, because we can be taken as a function of u dash and v dash. So dv is given by curl v by curl u dash into du dash plus curl v by curl v dash into dv dash. Now let us find the metric, which is by definition e dash du dash square plus 2f dash du dash dv dash plus g dash into dv dash square. Now substituting the values here, what is e dash? That is r1 dash dot r1 dash. F dash is r1 dash dot r2 dash. G dash is r2 dash dot r2 dash. So substituting the values of e dash, f dash and g dash, here we get the value which is in the form of whole square. So this is r1 dash du dash plus r2 dash dv dash whole square. Now let us use the equations 1 and 2. So using the equations 1 and 2, we get r1 into curl u by curl u dash plus r2 into curl v by curl u dash into du dash plus r1 into curl u by curl v dash plus r2 into curl v by curl v dash into dv dash whole square. Now let us combine the terms with r1 and r2. The terms in r1 are this term and this term, and the terms in r2 are this term and this term. Combining the terms and using the equations 3 and 4. Now from the equation 3, this expression is du and this expression is dv. So we put the values from equations 3 and from here we get r1 into du plus r2 into dv whole square. Now if we expand this whole square, this is r1 square du square plus 2 times r1 dot r2 into du dv plus r2 square dv square. Now what is r1 square? That is vector r1 dot vector r1, which is E, first fundamental coefficient, r1 dot r2, that is F, second fundamental coefficient, and G is r2 dot r2. Substituting the values here, so we have obtained E dash du dash square plus 2F dash du dash dv dash plus G dash dv dash square is equal to the original form, which was before the transformation of parameters. So we have proved that after applying the transformation, the new form obtained is same as the form which was before applying the transformation on the parameters. So this property is called invariance property, or we can say that metric is invariant. Next we define element of area on a surface at a point UV. So to define the element of area, let us consider a figure PQRS. Let us take the coordinates of the P point as UV, the coordinates of Q, U plus DU and V, the coordinates of R, U plus DU and V plus dV, the coordinates of S, RU and V plus dV. So these are joined by the four parametric curves. Now let us find the area of this parallelogram PQRS. To find its area, we require the two adjacent sides of this parallelogram. So let us find the vector PQ and the vector PS. Now vector PQ, by definition, vector PQ means position vector of Q minus position vector of P. Now position vector of Q and this is a position vector of P. So now expanding this term by Taylor's theorem and neglecting the second and higher order terms, so we get this expression. From here these two terms are cancelled out and this is by definition the vector r1. So vector PQ is equal to vector r1 into du. In the same way, by using the definition of the position vector and using the Taylor's theorem again, we get the value of this vector PS, which is r2 into dv. Now we have obtained two adjacent sides of the parallelogram. So by definition, area of the parallelogram is given by the cross product of the two vectors and its magnitude. So area ds is given by r1 du cross r2 dv, its magnitude. Now from here we can write this term as r1 cross r2 magnitude into du dv. Now by definition, the magnitude of r1 cross r2, that is h. So this is h du dv. So this is the formula for the element of area on a given surface at the point P having the coordinates u and v. Now the last formula is angle between two parametric curves. So to find the formula for the angle between two parametric curves, let us take two parametric curves. One curve is u is equal to constant and second curve is v is equal to constant. Let us take P is their point of intersection. Now as we already know, the angle between two curves is angle between their tangents. So let us find the angle between their tangents. So let us draw tangents at these two curves. So this is the tangent corresponding to the curve u is equal to constant and this is the tangent corresponding to the curve v is equal to constant. These tangents we have denoted by r1 and r2. Now if we find the angle between r1 and r2, that will be the angle between the given parametric curves. Let us denote this angle by the symbol omega. Now by definition of dot product of two vectors, we can find cos of the angle between r1 and r2. Now by definition we know that cos theta is given by r1 dot r2 divided by the magnitude of these two vectors. Now by definition r1 dot r2, that is f, r1 magnitude, that is under root e, r2 magnitude, that is under root g. So this is the angle between the two tangents and we can say that this is also the angle between the given parametric curves. We can also find the angle by using the definition of cross product of two vectors. By definition, R1 cross R2 magnitude is given by R1 magnitude into R2 magnitude into sine of the angle between the two vectors. So by that definition also, we can find the value of the angle between the two parametric curves. Now by definition, R1 cross R2 magnitude, that is H. This is under root E, this is under root G. And by definition, H square is Eg minus F square. So H will be under root of Eg minus F square. So substituting the value here, we get this is sine omega. Now dividing sine omega and cos omega, we get tangent omega, which is given by H upon F. So this is the angle between the parametric curves. In particular case, when the two parametric curves are orthogonal, means they cut each other at right angle. In that case, from the last equation, from this equation, if omega is 90, cos 90, that will be 0. So in that case, this quantity will be 0. So in that case, we get f is equal to 0. So these were the properties for the angle between the parametric curves. Thank you.